In the beginning, there was darkness. Not the silence of emptiness, but the silence of mystery. For as long as humans have walked beneath the night sky, we have looked upward and wondered. We traced patterns in the stars. We told stories about glowing dots scattered across endless black. We imagined gods, monsters, and distant realms hidden beyond the veil of darkness. But behind every myth and every legend lived a single question. Are we alone? This question is older than civilization, older than language, older than memory itself. Every generation has asked it. Every culture has shaped it differently, yet the meaning remains the same. A longing to know whether consciousness exists beyond this small, fragile planet we call home. For thousands of years we had only our eyes, and our eyes could see so little. The stars appeared fixed, the heavens seemed eternal. The universe felt small, finite, and centered around Earth. Humanity believed it stood at the center of creation, watched over by cosmic forces. Then came telescopes. Suddenly, the universe expanded. Galaxies revealed themselves. Nebulae bloomed like cosmic storms. Entire star systems appeared where once there had been darkness. Humanity realized that Earth was not the center, not even close. We were standing on a tiny rock orbiting an average star, in a galaxy among hundreds of billions of galaxies. The universe was not small. It was unimaginably vast. And in that vastness, the question grew louder. If the universe is so big, how could we possibly be alone? By the 20th century, imagination began to transform into science. Astronomers no longer only observed stars. They began to ask deeper questions. Could planets exist around other suns? Could those planets hold water? Could chemistry similar to Earth's give rise to life? For centuries, planets beyond our solar system remained pure speculation. There was no way to see them. Stars were simply too bright, their planets drowned in glare. But in the late 20th century, everything changed. Scientists developed sensitive instruments capable of detecting minute shifts in starlight, tiny wobble caused by orbiting planets. These early methods uncovered the first confirmed exoplanets. Worlds beyond our solar system were no longer hypothetical. They were real, and they were everywhere. Thousands of planets soon emerged from the data. Gas giants larger than Jupiter, rocky worlds smaller than Earth, planets orbiting close enough to their stars to melt metal, others drifting in frozen darkness. The universe was filled with planets. If planets were common, then perhaps life might be as well. But how could we detect life across unimaginable distances? Life leaves fingerprints. On Earth, living organisms constantly reshape the atmosphere. Plants produce oxygen, microbes release methane, animals exhale carbon dioxide. Over time, life transforms planetary chemistry. If we could read the atmospheres of distant planets, perhaps we could glimpse those same fingerprints. But to do that, we needed a telescope unlike any before. In 1990, humanity placed a revolutionary instrument into orbit. Free from Earth's turbulent atmosphere, it floated above clouds, storms, and pollution, peering directly into the depths of space. This telescope would transform astronomy forever. It revealed galaxies forming shortly after the Big Bang. It mapped starbirth inside nebulae. It measured the expansion of the universe. But among its many missions, one stood above all others: the search for life beyond Earth. From its vantage point in orbit, this telescope could analyze starlight with unprecedented precision. And hidden within that light were chemical fingerprints, the clues scientists had waited centuries to read. When a planet passes in front of its star, a small portion of the starlight filters through the planet's atmosphere before reaching our telescopes. This atmosphere absorbs specific wavelengths of light depending on its chemical composition. Water absorbs one set of wavelengths. Oxygen absorbs another. Methane absorbs yet another. By analyzing how the starlight changes, scientists can reconstruct the chemical makeup of alien skies. It is an extraordinary achievement. From tens or hundreds of light years away, we can determine whether a distant planet has clouds, storms, water vapor, and even complex molecules. This method transformed astronomy into planetary science. We were no longer merely observing stars. We were studying worlds. Scientists detected massive planets so close to their stars that their atmospheres were boiling into space. They observed giant clouds of hydrogen escaping into cosmic vacuum. They found planets where rain might fall sideways, driven by supersonic winds. Then came water vapor. Not oceans, not rivers, but water vapor suspended in alien skies. The implications were profound. Water is fundamental to life as we know it. Where water exists, chemistry flourishes. Complexity becomes possible. These discoveries electrified the scientific community. They also ignited public imagination. For the first time in history, humanity had proof that planetary atmospheres beyond our solar system could be measured, and that some of those atmospheres contained ingredients essential for life. But ingredients alone do not make a living world. The universe is an expert illusionist. Many chemical signals that suggest life can also be produced through geological and photochemical processes. Volcanoes can release methane. Ultraviolet radiation can split water molecules, producing oxygen. Exotic chemistry can mimic biological fingerprints. To claim life, scientists require overwhelming evidence, not one signal, but many appearing together, sustained over time, resistant to non-biological explanation. This cautious approach protects science from error, but it also frustrates public expectation. Headlines often proclaim, "Alien life discovered." Reality is far more careful. What scientists actually find are possible biosignatures, chemical hints that life might exist. And this difference matters, because history is full of near misses. In several famous cases, chemical detections initially sparked worldwide excitement, only to collapse under deeper analysis. Data once interpreted as biological later revealed alternative explanations. Instrumentation errors, stellar interference, noise disguised as signal. Each time, disappointment followed. But each time, science improved. Better calibration methods, more precise instruments, more sophisticated models. False positives taught scientists how not to be fooled. And with each lesson, confidence grew that one day, when life is truly detected, the evidence will be undeniable. As data accumulated, scientists realized something staggering. Planets are everywhere. On average, every star in our galaxy hosts at least one planet. This means that, within the Milky Way alone, a galaxy containing over 200 billion stars, there may be hundreds of billions of planets. Among them, billions could be rocky. Millions may lie in habitable zones. Even if life arises on only a tiny fraction of suitable worlds, the numbers suggest that living planets could be abundant. The universe no longer seems empty. It seems crowded. As discoveries multiplied, so did ambition. Scientists began targeting planets that closely resemble Earth. Rocky, temperate, orbiting stable stars. Worlds where liquid water could persist. These targets became prime candidates in the search for biosignatures. Among them, one planet captured global attention. A super-Earth orbiting a red dwarf star, 120 light-years away. Its atmosphere showed water vapor and methane. two gases deeply connected to life on Earth. The possibility electrified researchers. Yet caution prevailed. The planet's temperature, atmospheric pressure, and radiation environment remained uncertain. The signals were intriguing, not conclusive. Once again, hope balanced delicately against skepticism. Why does the discovery of alien life matter so deeply? Because it challenges the story we tell ourselves about existence. For centuries, humanity believed it was unique, special, chosen, the center of cosmic purpose. But every major astronomical discovery has humbled us. Earth is not the center of the solar system. The sun is not the center of the galaxy. The Milky Way is not the center of the universe. With each revelation, we are pushed farther from cosmic centrality. Yet paradoxically, the search for life beyond Earth restores meaning. If life exists elsewhere, then life is not an accident. It is a cosmic process, a natural unfolding of chemistry and physics. We become part of a living universe, not a lonely anomaly. And that realization changes everything. Detecting life would reshape religion, philosophy, politics, and identity. It would force humanity to confront its place in a populated cosmos. Are we just one voice among countless others? Are intelligence and consciousness inevitable outcomes of cosmic evolution? Or are we a rare flicker in endless darkness? These questions haunt every observation. They hover behind every data set. They turn scientific inquiry into existential exploration. Today, humanity stands closer than ever before to answering its oldest question. Our telescopes can now probe planetary atmospheres with extraordinary sensitivity. New observatories extend vision into deeper wavelengths. Artificial intelligence helps decode complex spectral data. Space agencies plan missions capable of directly imaging Earth-like worlds. Each technological leap tightens the noose around uncertainty. We are approaching a moment in history when speculation will finally give way to evidence. And yet, the universe remains silent, for now. But silence is not emptiness. It is anticipation. It is the pause before revelation. And in that pause, humanity continues to look. The story of the search for alien life is not a story of answers. It is a story of patience, of humility, of relentless curiosity. Across centuries, across civilizations, across generations, humans have lifted their eyes to the night sky and wondered. Now, at last, we possess the tools to listen back. This is only the beginning. Because beyond this threshold lie discoveries that may redefine life itself. And the universe is preparing to speak. We learn to see planets not by their light, but by how they steal it. When a distant world crosses the face of its star, a tiny fraction of that starlight vanishes. The change is almost imperceptible, smaller than a heartbeat in cosmic time. Yet hidden inside that faint dimming is a story. The light that survives the journey, filtered through a thin veil of alien air, carries chemical fingerprints. Each molecule leaves its own shadow in the spectrum. Each shadow becomes a letter in a language written across the universe. This is how we began to read alien skies. At first, the technique seemed impossible. Stars are unimaginably bright. Planets are faint. The difference in brightness is so extreme that it is like trying to spot a firefly circling a lighthouse from thousands of kilometers away. Yet precision instruments, careful calibration, and mathematical patience made it possible. Scientists learned to detect changes smaller than 1%, then smaller than 0.1%, then smaller than 1/100th. Each improvement unlocked new detail. When starlight passed through a planet's atmosphere, specific wavelengths disappeared. Water absorbed infrared light. Sodium left sharp yellow imprints. Methane carved delicate troughs. By analyzing these missing wavelengths, scientists reconstructed the composition of worlds they could not see directly. It was as if the universe had allowed us to read postcards sent from planets across the void. The earliest atmospheric detections focused on massive gas giants. These worlds were easiest to study because their large sizes blocked more starlight. Many orbited extremely close to their stars, completing entire orbits in just days. Their skies were furnace hot, whipped by winds faster than any hurricane on Earth. Some were so close that their atmospheres were being torn away. Observations revealed giant tails of hydrogen streaming behind these planets like comet trails. Stellar radiation blasted their upper atmospheres, heating gases until they escaped into space. Entire worlds were slowly evaporating before our eyes. It was violent. It was beautiful. And it revealed something essential. Planetary atmospheres were dynamic, fragile, and alive with motion. Soon after, scientists detected water vapor. The announcement echoed through observatories, laboratories, and newsrooms. Water was no longer confined to Earth and our solar system. It existed in distant skies, orbiting foreign suns. But these early water detections were not signs of oceans or rain. They were wisps of vapor suspended in blistering heat. The worlds themselves were hostile, far too hot for life as we know it. Still, the presence of water confirmed something crucial. The raw ingredients of life were widespread. And where ingredients exist, chemistry follows. The next challenge was finding smaller planets. Rocky planets. Worlds closer to Earth in size and temperature. These were far more difficult to detect. Their atmospheres were thin, their transits barely altered starlight. Their signals were buried in noise. Years passed. Data accumulated. Analysis methods sharpened. Slowly, cautiously, the first atmospheric hints emerged from smaller worlds. One planet, orbiting a red dwarf star deep in the constellation Leo, drew extraordinary attention. Its mass suggested a world larger than Earth, but smaller than Neptune. A super-Earth, or mini-Neptune. More importantly, its orbit placed it in the star's temperate zone, where liquid water could theoretically exist. Spectral analysis revealed water vapor. It also revealed methane. On Earth, methane is deeply associated with biology. Microbes generate it in oxygen-poor environments. Animals release it through digestion. Wetlands breathe it into the air. While geological processes can also produce methane, sustained atmospheric methane often implies replenishment. For the first time, scientists glimpsed a world whose atmosphere contained a combination of gases that, together, sparked intense interest. The data did not prove life, but it whispered possibility. Soon, other planets joined the list. Cloudy skies, exotic chemistry, atmospheres containing sodium, potassium, carbon monoxide, carbon dioxide, and water. Each detection expanded the catalogue of planetary diversity. Some worlds appeared to have skies filled with haze, masking deeper layers. Others showed dramatic day-night temperature contrasts. Some exhibited violent storms. Others revealed astonishing stability. No two worlds looked the same. And that realization reshaped planetary science. Planets were not mere variations of those in our solar system. They were entire ecosystems of physics and chemistry, each governed by its own balance of radiation, gravity, composition, and history. Understanding these atmospheres required not just observation, but theory. Scientists built atmospheric models simulating temperatures, wind patterns, chemical reactions, and cloud formation. They tested these models against data, refining them again and again. Slowly, patterns emerged. They learned how starlight interacts with gases. They learned how ultraviolet radiation can split molecules apart. They learned how stellar activity can masquerade as atmospheric features. And in learning these things, they also learned how easy it is to be deceived. Stars are not static light bulbs. They flare, they pulse, they erupt. Their surfaces ripple with magnetic storms. These stellar behaviors imprint signals onto the light we receive, signals that can easily be mistaken for planetary features. Separating star from planet became one of the greatest challenges in exoplanet science. It required repeated observations, long-term monitoring, and complex statistical methods. False detections occurred. Spectral lines once thought to indicate water later proved to be stellar artifacts. Signals attributed to atmospheres vanished under closer scrutiny. Each mistake was painful. Each correction was necessary. This relentless skepticism is what protects science from illusion, because extraordinary claims demand extraordinary evidence. Yet, amid caution, progress continued. New observing techniques emerged. High dispersion spectroscopy allowed scientists to resolve individual molecular lines with unprecedented clarity. Phase curve analysis revealed temperature maps across planetary surfaces. Polarimetry measured how light scattered in alien skies, hinting at cloud composition. The more we learned, the more subtle the search became. No longer were scientists looking for a single molecule. They sought atmospheric imbalance. On Earth, life pushes chemistry far from equilibrium. Oxygen and methane coexist despite reacting rapidly with each other. Their continued presence signals constant biological replenishment. A similar imbalance on another planet would be difficult to explain through geology alone. This concept reshaped the search. Rather than hunting isolated molecules, scientists searched for chemical patterns that defied natural equilibrium. But the universe once again proved cunning. Non-biological processes could generate oxygen in surprising ways. Intense ultraviolet radiation could split water molecules, allowing hydrogen to escape and oxygen to accumulate. Planetary surfaces rich in certain minerals could catalyze unusual chemical cycles. Methane could emerge from volcanic activity. Even complex molecules could arise from photochemical reactions. The line between biological and abiotic chemistry blurred. This forced scientists to raise their standards. It was no longer enough to detect promising gases. They needed context. They needed planetary mass, temperature, radiation environment, geological models, and stellar behavior. Every detection became part of a vast puzzle. As instruments improved, so did ambition. Astronomers began searching for Earth-like worlds around smaller, cooler stars. These stars, known as red dwarfs, offered advantages. Their planets orbit close, increasing transit frequency and detection sensitivity. But red dwarfs also presented dangers. They are active. They flare violently. Their radiation can strip atmospheres and sterilize surfaces. Still, their abundance made them irresistible targets. Many of the most promising candidates orbit such stars. One after another, new worlds entered scientific consciousness. Some had thick clouds. Some had surprisingly clear skies. Some appeared to possess stable atmospheres. Each added a brushstroke to a growing cosmic mural. Yet, with each discovery came headlines. And headlines often outran reality. Phrases like Earth 2.0 and alien life detected spread rapidly. Public excitement surged, expectations soared. Then, inevitably, reality tempered them. Further observations revised conclusions. Uncertainties expanded. Signals weakened. Excitement dimmed. This cycle repeated again and again, and it revealed a profound tension. Humanity's hunger for discovery versus science's devotion to restraint. The media craves definitive answers. Science provides probabilities. The media seeks drama. Science seeks truth. Between them lies misunderstanding. Yet despite confusion, progress continued. Every dataset improved models. Every correction refined technique. Every near miss strengthened methodology. Gradually, astronomers assembled a framework for evaluating potential biosignatures. They developed rigorous criteria: multiple gases, chemical disequilibrium, planetary context, stellar characterization, independent verification. Only when all these conditions converge would scientists seriously consider a detection credible. And even then, skepticism would remain, because the cost of error is immense. To announce life beyond Earth prematurely would undermine public trust and scientific integrity. Better to wait. Better to be certain. While the search unfolded, technological ambitions surged. Next-generation instruments promised sensitivity beyond anything before. Infrared observatories capable of peering deeper into planetary atmospheres. Spectrographs capable of resolving individual molecular vibrations. Coronagraphs designed to suppress starlight and reveal faint planetary glimmers. Even star-shade concepts. Massive structures flying tens of thousands of kilometers from telescopes to block starlight and allow direct imaging of Earth-like worlds. These technologies would not merely hint, they would interrogate. They would dissect planetary atmospheres molecule by molecule. They would measure seasonal changes, cloud cycles, and chemical fluctuations. They would watch alien weather unfold, and perhaps one day they would glimpse the unmistakable breath of biology. Yet even as technology races forward, humility remains central. Scientists understand that life elsewhere may not resemble life on Earth. It may not rely on oxygen. It may not produce methane. It may use chemistry entirely unfamiliar. Thus, the search for life is also a search for broader definitions of habitability. What does life require? Energy, complex chemistry, stability. But beyond that, our assumptions remain narrow. Some speculate about silicon-based life. Others imagine ammonia oceans. Others envision exotic metabolisms thriving in high radiation or extreme temperatures. The universe may host biologies beyond our imagination, and that possibility demands open-mindedness. The search is not merely for mirrors of Earth. It is for novelty, for difference, for forms of organization that challenge our definitions. In this way, the hunt for alien life becomes a philosophical journey. It forces humanity to question its own uniqueness, its own assumptions, its own limits of understanding. Each discovery, each data set, each faint spectral line becomes part of a deeper narrative. A narrative about how life might arise wherever chemistry and energy permit. Yet despite decades of searching, one truth remains. We have not yet heard a clear answer. No unmistakable signal. No undeniable fingerprint. No spectral shout declaring, "You are not alone." Instead, we hear whispers, hints, possibilities. And those whispers fuel both wonder and patience. Because in science, patience is not delay. It is discipline. It is the willingness to wait for certainty rather than settle for hope. The universe has waited nearly 14 billion years. It can wait a little longer. And so can we. We continue to build better instruments. We refine our methods. We sharpen our questions. And we look. Always we look. Because the moment when evidence becomes undeniable, when chemical imbalance resists all alternative explanation, will mark one of the greatest turning points in human history. Until then, the search continues. Quietly, relentlessly, with humility, with wonder, with disciplined imagination. And somewhere in the vast darkness between stars, a world may already be whispering its story into the fabric of light. waiting for us to learn how to listen. This is not the end of the search. It is the sharpening of it. And the universe is growing louder. In the vast silence of space, patterns emerge that tempt interpretation. A faint dip in light, a subtle chemical signature, a whisper of molecules that, on Earth, belong to living systems. But the universe is a master of illusion. It can craft signals that resemble life without ever hosting it. And nowhere is this more evident than in the long history of false positives. Moments when humanity believed it stood on the brink of discovery, only to step back into uncertainty. Science advances not through certainty, but through correction. The road toward detecting alien life is paved with misinterpretations, revisions, and humility. Each false alarm sharpens our understanding. Each disappointment strengthens our methods. And in the slow refinement of error, truth begins to emerge. At the heart of this struggle lies chemistry. Life reshapes its environment. It disrupts chemical balance. On Earth, living organisms maintain an atmosphere far from equilibrium. Oxygen and methane coexist despite reacting violently with each other. Their continuous replenishment requires biological activity. Without life, these gases would vanish within thousands of years. This imbalance became the guiding principle in the search for biosignatures. If scientists could detect similar disequilibrium on another world, it might point toward life. But chemistry is complex, and the universe is capable of astonishing mimicry. Oxygen, long considered one of the strongest indicators of life, can accumulate without biology. Ultraviolet radiation from a star can split water molecules, allowing hydrogen to escape into space, while oxygen builds up. Over millions of years, this process can generate oxygen-rich atmospheres on lifeless planets. Likewise, methane can be produced through geological processes. Volcanoes release it. Hydrothermal vents synthesize it. Chemical reactions deep within planetary crusts can generate it without any biological involvement. Even combinations of gases once thought impossible without life have been reproduced in laboratory simulations. Each discovery of an abiotic pathway complicates the search. It becomes increasingly difficult to separate living chemistry from cosmic chemistry. And so, scientists build ever more detailed models, exploring every conceivable non-biological explanation. The moment a promising signal appears, the real work begins. Independent teams reanalyze the data. Alternative hypotheses are tested. Instrument artifacts are examined. Stellar contamination is evaluated. Every variable is questioned. Because science does not aim to confirm belief, it aims to dismantle it. Only what survives destruction earns acceptance. This ruthless skepticism is not cynicism. It is discipline, and it is what makes discovery meaningful. Throughout the history of astronomy, false positives have served as powerful teachers. In the late 20th century, early radio surveys searching for intelligent signals detected strange bursts of radiation. For a moment, the world wondered if contact had been made, but further analysis revealed earthly interference, signals bouncing between satellites and ground stations. More recently, unusual spectral lines sparked intense excitement, suggesting exotic chemistry. Months later, calibration errors were identified. The signals evaporated. Even potential detections of simple molecules have collapsed under scrutiny. What initially appears clear often dissolves into ambiguity. One of the most dramatic examples involved the detection of a gas rarely found on Earth outside biological systems. Its presence in the atmosphere of a nearby planet ignited global headlines. For weeks, speculation soared. Could this be the first true sign of alien life? Scientists debated fiercely. Some argued that geological mechanisms could explain it. Others insisted the quantities detected defied known abiotic processes. Telescopes turned toward the planet again. New data arrived. The signal weakened. Statistical confidence fell. The discovery faded into uncertainty. What remained was not failure, but education. Each such episode refines scientific caution. Each teaches astronomers where mistakes hide. Noise masquerades as signal. Instrument sensitivity exaggerates weak features. Stellar variability bleeds into planetary spectra. Even cosmic dust can generate misleading signatures. Separating planet from star, life from chemistry, reality from illusion becomes a monumental challenge. This is why no single observation is ever enough. True discovery demands repetition, consistency, verification, years of monitoring, different instruments, different wavelengths. Only when signals persist across independent methods does confidence rise. And even then, caution remains. Because the greatest danger in science is not ignorance. It is premature certainty. The pressure to announce groundbreaking discoveries is immense. Funding, recognition, public interest, career advancement, all reward bold claims, yet the cost of being wrong is equally high. False discoveries erode trust. They damage credibility. They distort public understanding. Thus, the scientific community polices itself with relentless rigor. Peer review dissects methodology. Replication challenges conclusions. Statistical scrutiny hunts hidden biases. No claim survives untested. And in this environment, only the strongest evidence endures. Yet even amid restraint, the search presses forward. Technology evolves. Instruments grow more precise. Data becomes richer. Where once scientists could barely detect planetary transits, they now resolve atmospheric layers. Where once molecules blurred together, they now separate into distinct spectral fingerprints. Each technological leap sharpens perception, and with sharper perception comes new complexity. More detail reveals more uncertainty. More resolution exposes new confounding factors. The deeper we look, the more the universe reminds us of its complexity. Stellar activity emerges as one of the greatest obstacles. Many promising planets orbit small stars which flare violently. These flares alter stellar spectra, injecting noise into observations. They ionize planetary atmospheres. They trigger chemical reactions that produce misleading biosignatures. A planet bathed in relentless stellar radiation may accumulate oxygen through water photolysis, mimicking biological production. At the same time, intense radiation can strip atmospheres entirely, rendering planets barren. Understanding stellar behavior becomes as crucial as understanding planetary chemistry. Thus, astronomers now study stars as carefully as planets. Magnetic fields, flare cycles, rotation periods, surface granulation. Every stellar detail matters. Without stellar characterization, planetary interpretation collapses. Even planetary surfaces complicate matters. Certain minerals can catalyze chemical reactions that produce gases once thought exclusive to life. Exotic geologies may generate unexpected atmospheric compositions. A planet's internal heat, tectonic activity, and crustal chemistry influence its skies. Thus, biology is only one contributor among many. This realization forces a profound shift in thinking. Life may not be rare, but proving its presence may be extraordinarily difficult. And that difficulty demands patience. The universe does not yield its secrets easily. It tests our assumptions. It punishes haste. It rewards discipline. Across decades, scientists have learned to accept uncertainty not as failure, but as fidelity to truth. A tentative signal becomes a hypothesis. A hypothesis becomes an investigation. An investigation becomes a data set. And only through accumulation does clarity emerge. The path is slow, but it is steady. Beyond chemistry, another challenge arises. Life itself may be subtle. On Earth, life existed for billions of years before significantly altering the atmosphere. For nearly half of our planet's history, oxygen was scarce. Microbial life dominated, leaving faint chemical traces. If similar timelines unfold elsewhere, many living planets may appear lifeless from afar, their biosignatures too weak to detect, too fragile to survive stellar radiation, too transient to accumulate. Thus, absence of evidence is not evidence of absence. Many inhabited worlds may hide in chemical ambiguity. Their life too quiet to announce itself across interstellar distances. This possibility humbles astronomers. It suggests that the universe could teem with life, yet remain silent, because life does not necessarily shout. Sometimes it whispers, and sometimes it leaves no detectable trace at all. In this sense, the search for alien life confronts a paradox. The more we learn, the more difficult detection becomes. Greater understanding reveals deeper complexity. Better instruments uncover more confounding factors. Improved models generate alternative explanations. Each advance narrows the window of certainty. Yet paradoxically, this narrowing strengthens confidence. When life is finally detected, the evidence will have survived unimaginable scrutiny. It will stand unassailable. Until then, scientists remain cautious. They speak in probabilities, in confidence intervals, in statistical significance. They resist definitive language, not because they lack imagination, but because they respect reality. In laboratories across the world, experiments simulate alien atmospheres. Researchers recreate exotic chemical environments. They expose gas mixtures to ultraviolet radiation. They test how molecules interact under extreme pressures and temperatures. These experiments reveal surprising pathways, unexpected reactions, novel compounds. The universe's chemical creativity surpasses our assumptions. Each laboratory result refines atmospheric models. Each simulation reveals new false positives. Each discovery complicates interpretation. And yet within this complexity lies hope, because life also exhibits complexity. Its chemistry is dynamic, adaptive, and patterned. Its influence persists. Over time, life carves unmistakable signatures. Forests alter carbon cycles. Oceans regulate temperature. Microbes reshape atmospheric composition. On a planetary scale, life becomes geological. If such processes occur elsewhere, they may eventually announce themselves, not as isolated molecules, but as planetary transformations. This insight shifts the search toward long-term stability. Instead of hunting fleeting gases, scientists seek enduring patterns. They examine climate regulation, atmospheric cycling, seasonal variations, surface reflectivity, even subtle changes in color across planetary orbits. These phenomena, taken together, may reveal living systems at work. For example, vegetation on Earth reflects near-infrared light in a distinctive way, producing what scientists call the red edge. If similar biological pigments exist elsewhere, their spectral signatures might betray their presence. Such ideas push the boundaries of detection. They demand extraordinary sensitivity. They require patient observation across years. But they offer a tantalizing possibility, detecting life not by its breath, but by its skin. As technology advances, new missions are designed around these concepts. Large space observatories, advanced coronagraphs, interferometric arrays. star shades drifting in formation. Each aims to directly image Earth-like worlds, to separate planetary light from stellar glare, to analyze surfaces and atmospheres in unprecedented detail. These future instruments promise a qualitative leap. They may reveal continents, oceans, cloud systems, seasonal cycles. They may glimpse the faint glimmer of life reflected across interstellar distances. Yet even as ambition grows, humility remains essential. Because nature rarely conforms to expectation. Each time we believe we understand the universe, it surprises us. When astronomers expected uniform planetary systems, they found chaos. When they predicted rare planets, they found abundance. When they anticipated simple atmospheres, they found complexity. The search for alien life will likely follow the same pattern. Discovery may arrive from unexpected quarters, from planets unlike Earth, from environments once thought hostile, from chemistry unfamiliar to terrestrial biology. Thus, scientists cultivate openness. They expand definitions. They challenge assumptions. They accept uncertainty as a guide rather than an obstacle. This intellectual flexibility becomes the true instrument of discovery. The universe does not reveal itself to rigid minds. It yields to those willing to revise belief. And so, the history of false positives becomes not a catalogue of failure, but a chronicle of learning. Each mistaken claim strengthens future certainty. Each retracted headline sharpens methodological rigor. Each disappointment fortifies patience. This discipline ensures that when life is finally detected, the announcement will carry weight. It will not be speculative. It will not be sensational. It will be devastatingly precise, and its impact will ripple through every domain of human thought. But until that moment arrives, science remains suspended between anticipation and restraint. Search continues. Observations accumulate. Models refine. The universe watches silently, and humanity waits, not in despair, but in disciplined hope. Because in science, hope is not belief. It is persistence. It is the quiet determination to keep looking, even when the darkness offers no answer. Yet, imagine for a moment that the signal finally arrives. Not as a whisper, not as a fragile hint buried in noise, but as a clear, persistent pattern. A spectral signature that refuses every non-biological explanation. A chemical imbalance so profound, so stable, so enduring, that no known geological or photochemical process can account for it. Imagine the moment when uncertainty collapses. For the first time in human history, we would know. Not suspect, not hope, not theorize, but know with scientific certainty that life exists beyond Earth. The announcement would not arrive with thunder. There would be no cosmic trumpet. No blinding flash. Just a quiet press release. A carefully worded paper. A cautious statement framed in probabilities. And yet, its impact would ripple across the planet. In laboratories, scientists would sit in stunned silence. In observatories, researchers would stare at screens, reading the same lines again and again, unable to believe that the data truly held. Across the world, newsrooms would scramble. Headlines would form. Broadcasts would interrupt programming. Social networks would erupt. And in countless homes, people would pause, lift their eyes, and feel something shift deep within themselves. Because at that moment, humanity would cross an invisible boundary. We would no longer be alone. For thousands of years, every philosophy, every religion, every myth, and every system of meaning has been shaped by the assumption of solitude. We are the thinking species, the only conscious voice in a silent universe. the center of awareness in infinite darkness. But that story would change. Suddenly, consciousness would no longer be unique. Life would no longer be exclusive. We would become part of a larger biological narrative, one that stretches across stars and galaxies, binding worlds together through the shared chemistry and cosmic evolution. This realization would not diminish humanity. It would expand it. Our story would no longer end at Earth's atmosphere. It would continue across light years. And in that expansion, ancient questions would gain new depth. What does it mean to be human in a living universe? Are intelligence and consciousness inevitable? Or are they rare accidents? Does life emerge wherever conditions allow, or only under extraordinary circumstances? The discovery of even microbial life elsewhere would suggest that life is common, that the universe is biologically fertile. It would imply that biology is not a cosmic anomaly, but a natural outcome of chemistry and physics. Life would become a universal process. Not a miracle, not a fluke, but a pattern. Yet if complex life were found, multicellular organisms, ecosystems, or even intelligence, the implications would be even more profound. Such a discovery would challenge our understanding of evolution. It would force us to confront the possibility that intelligence may arise again and again, shaped by natural selection toward awareness, curiosity, and perhaps even culture. We would no longer be the universe contemplating itself for the first time. We would be one voice among many. This realization would ripple through philosophy. For centuries, humans have wrestled with their place in existence. Are we central? Are we special? Are we purposeful? The discovery of alien life would reshape these debates. It would dissolve the illusion of cosmic centrality, but it would not erase meaning. Instead, it would redefine it. Meaning would no longer derive from exclusivity. It would emerge from connection, from belonging to a vast, unfolding tapestry of life. Our ethical frameworks would shift. If life exists elsewhere, does it possess rights? Do microbial ecosystems deserve protection? Do alien biospheres hold intrinsic value? What obligations would humanity have toward living worlds beyond Earth? Would exploration become stewardship? Would expansion require restraint? These questions would not remain theoretical. As technology advances, humanity will gain the power to reach other star systems. If not physically, then through probes, telescopes, and perhaps one day, robotic explorers. How we treat discovered life will reflect who we are. Will we approach as conquerors or as caretakers? History offers caution. On Earth, contact between civilizations has often led to exploitation, destruction, and extinction. In space, the stakes would be far higher. An entire alien biosphere could vanish beneath careless contamination. Thus, planetary protection becomes not merely technical, but moral. The discovery of life elsewhere would impose a new ethical horizon, one that demands humility, one that requires patience, one that challenges humanity to rise above its own instincts. Religious traditions would also confront transformation. Some might struggle, others would adapt. Many faiths already contemplate vast universes filled with divine creation. The existence of alien life need not negate spiritual belief. It may deepen it. For some, it would affirm a creator's boundless imagination. For others, it would reaffirm the sacredness of life itself. New theologies would emerge. New interpretations would flourish. And ancient doctrines would find new relevance. Because at its heart, religion seeks meaning. And the discovery of life beyond Earth would offer meaning on a cosmic scale. It would invite humanity to see itself not as isolated, but as interconnected. one branch in a forest of living worlds. Art and culture would transform. Writers would imagine alien histories. Musicians would compose cosmic symphonies. Painters would depict skies beneath foreign suns. Cinema would shift from speculation to interpretation. Human creativity would surge, because inspiration thrives on expanded horizons. And nothing expands the horizon more than realizing we are part of a living universe. Even politics would feel the tremors. National rivalries might shrink beneath planetary identity. Earth could begin to see itself as a single world, one civilization, one species. The discovery of alien life would not erase conflict overnight, but it could reframe priorities. In the presence of cosmic company, human differences might seem smaller. Our shared fragility might feel more urgent. Environmental stewardship might gain new weight. Because if life is precious on Earth, it is precious everywhere. And our planet, shimmering blue in the darkness, might be seen more clearly than ever before. The fragile oasis it truly is. The scientific consequences would be staggering. Biology would become a comparative science. Evolutionary theory would expand. Astrobiology would mature. Chemistry would be rewritten. New molecular pathways would challenge established frameworks. Life's adaptability would astonish. The boundaries of habitability would stretch. And with each new insight, humanity's understanding of itself would deepen. What traits are universal? What traits are unique? Which aspects of biology are inevitable? Which are contingent? Are eyes common? Are brains typical? Is intelligence rare? These questions, once confined to Earth, would become cosmic inquiries. Even mortality might feel different. If life is abundant, then existence itself becomes more enduring. Civilizations may rise and fall, but life persists. Across planets, across stars, across epochs. In this light, humanity's brief moment becomes part of a much larger story, one that began long before Earth formed and will continue long after our species fades. This perspective humbles, but it also liberates. It invites us to see ourselves as participants, not proprietors, of cosmic life. And in that participation lies responsibility. Responsibility to protect. Responsibility to preserve. Responsibility to explore with care. Because discovery is power. And power, untempered by wisdom, becomes destruction. Thus, the ultimate question is not whether we can find life. It is how we will respond when we do. Will we approach with wonder or with fear? Will we embrace connection or retreat into isolation? The universe will not dictate our answer. That choice belongs to us. And perhaps in this way, the search for alien life is also a search for human maturity. It tests our patience. It challenges our ego. It asks us to consider ourselves not as masters of creation, but as members of it. The technology that makes discovery possible is advancing rapidly. Future observatories will image Earth-like planets directly. They will map continents. They will track weather systems. They will observe seasonal cycles. They will detect vegetation patterns. They may even identify industrial pollution, the faint signatures of alien civilizations reshaping their worlds. Each step brings humanity closer to a moment of reckoning, not with aliens, but with itself. Because the discovery of life elsewhere would force humanity to confront its own contradictions, our capacity for wonder and violence, our thirst for knowledge and dominance, our creativity and destructiveness. In the cosmic mirror, we would see ourselves more clearly. Perhaps that is the true purpose of the search, not merely to find others, but to understand ourselves. For centuries, humans gazed at the stars seeking meaning. They saw gods, they saw destiny, they saw fate. Now, with telescopes and equations, we see chemistry, physics, and biology. Yet the meaning remains. We still seek connection. We still yearn to belong. And the possibility that life exists elsewhere whispers that belonging may extend far beyond Earth. That our story is woven into a universal narrative, one that stretches across galaxies and epochs, one that binds all living things in a shared origin. From stardust to consciousness, from hydrogen to thought, every atom in our bodies was forged in ancient stars. Every molecule carries cosmic history. We are, quite literally, the universe become aware. And if life exists elsewhere, then awareness itself is a cosmic phenomenon, a pattern written into the laws of reality. The search for alien life is, in the end, a search for cosmic kinship, for evidence that the universe is not indifferent, that complexity emerges, that meaning can arise, and perhaps that hope is justified. As our instruments grow more powerful, our gaze extends further. Each year, new planets appear. New atmospheres are analyzed. New candidates emerge. The silence persists. But it feels different now. It no longer feels empty. It feels expectant, as if the universe is preparing an answer. And when that answer finally arrives, it will not merely tell us about distant worlds. It will tell us something profound about ourselves, that we are part of something vast, something ancient, something alive. Until then, humanity continues to listen. We build, we calculate, we observe, we wait, not with impatience, but with wonder. Because the greatest discoveries are rarely sudden, they are earned. Through centuries of curiosity, through generations of inquiry, through disciplined imagination, and perhaps one night under a quiet sky, a signal will arrive, a pattern in light, a whisper across space. And in that moment, the universe will speak, and humanity will finally know we were never alone.